The set A 1, 2 until 2045 contains 2045 elements. A subset S of A is called triple free if no element of S equals 3 times another element of X. For example, 1, 2, 4, 5, 10, 2, 0, 4, 3 is triple free, but 1, 2, 4, 5, 10, 6, 8, 1, 2, 0, 4, 3 is not triple free. The triple free subsets of A that contain the largest number of elements contain exactly 1, 5, 3, 5 elements. They are n triple free subsets of A that contain exactly 1, 5, 3, 5 elements. The integer n can be written in the form p to the power of a, q to the power of b, where p and q are distinct prime numbers and a and b are positive integers. If n capital is equal to p squared plus q squared plus a squared plus b squared, then the last 3 digits of capital N are. This question can be simplified, and we will do it in that simple way. The first thing, of course, is to understand that once you find the value of n, the rest is a piece of cake, because then you just have to deal with this algebra, and that's very easy. So we will concentrate really on just the first part of the question, concentrating on trying to find the value of this n. So first, let's start off with a small subset. That's a very big one, from 1 to 2045. It would take forever to explain and would become very confusing very quickly. So let's start off with a simple one with only 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, my k is 9, k representing the number of terms. Now my goal is to find triple free subsets. So triple free subsets from the definition are basically a subset where no element is 3 times another. So for example, I can't put 3 and 9 in a subset because 9 is 3 times 3. So I've got to make subsets that are triple free. The strategy is as follows, and once you understand the strategy, the question becomes a lot easier. Here we go. What you do is you break up this into different groups. The first group starting with 1 and triples. So 1 times 3, 3 times 3, like that. That's the first group. Then you go to the next number, 2, and do the same thing. 2 times 3 is 6. 6 times 3 is 18, but I don't need to worry about 18 because I'm only going up to 9. All right, let's keep going. Next one would be 3. Well, 3 is already included. Next one would be 4. 4 times 3 is 12. Well, that means 4 just appears by itself. 5 appears by itself, so does 6, and so does 7. Well, 6 actually I already have here, so don't include 6. So as you can see, you got to make sure you don't include things that have already been included. So these are my subsets. Now, to make a triple free, I have to choose one or more from each of these groups. I have to choose the max, because the key here is right here. The largest number of elements, that is the key. I have to make the subsets have the maximum amount. So I have to choose the maximum from each subset. From here, I can only choose one. I can only choose one number. Here, I can only choose one number. Here, I can only choose one number. But from here, I've got 2 choices, either the 2 or the 6. I got 2 choices. From here, it's not tricky, but you just have to do a little bit of thinking. What can I choose from here? Remember, I've got to choose it in a way so I make the maximum. Well, I can't choose 3 and 9 because 9 is 3 times 3. I can't choose 3 and 1. Those 2 can't be together. But I can choose 1 and 9. And there's only one way of doing that. Now you say, well, what about 1, 3, and 9? I can't do that because 9 is 3 times 3. And you say, well, what about just 3 by itself? No, because that would not make it the largest. I have to make it the largest. I'm forced to make the largest subset. I have to choose the most numbers from each of those subsets. So then what you do is you multiply these guys right here, and that gives you the total. So in this case, it's just 2. So what that means is that when k equals 9, I have 2 triple free subsets. And since there's only 2, we can just list them. We can easily list them 1, 9, 2, 4, 5, 7, 8, and 1, 9, 6, 4, 5, 7, 8. I didn't write them in chronological order. I'm just going by these subsets. Okay? So hopefully, with a very small example, you're kind of getting how this works. Now let's move up, not to the big one. Let's move up to a slightly bigger example. K equals 27. Now, I've got 1, 2, 3, and so on, right? All the way up until 26, 27. That's my big set. And then I've got to do the subsets, just like how I did here. Okay, starting with 1. 1, 3, 9, 27. Then let's go to 2. 2, 6, 18. Remember, I got to create these sets. 3 is already included. 4, multiplied by 3, 12, and then that's it. Can't go to 36 because my list only goes up to 27. 5, and 15, right? 5 times 3 is 15. 6 is already there. 7, yeah, that will be good. 7 times 3 is 21. 8, yes, 8 times 3 is 24. 9's already there. 10 times 3 is 30, but 30 goes beyond, so 10's going to appear by itself. And so will 11, so will 13. Skip over 12 because that's already there. So will 14, so will 16, 17, 19, 20, 22, 23, 24, and 26. Make sure I skip over ones that have already been included. Now, as we did before, let's figure out how many do we get. Well, from each of these individuals, you can only choose one, right? So 1, 1, 1, there's only one to choose from each of those subsets since there's only one number in the subset. But with these guys, there's 2. There's 2, 2, 2, and so on. Now we get to this guy, and as before, we can only choose 2 and 18. And I think I had explained that sort of in the same way there. When there's 3 elements, you can only choose it in one way, and that is you have to choose the 2 on the opposite ends. You can't choose, obviously, 8 and 16 because 18 is 3 times 6. You can't choose the 6 and 2 because 6 is 3 times 2. And you can't choose the 6 by itself, even though it's valid, because we want to make the maximum amount of terms in that subset, as I had previously explained. Now we come to this guy. This is new. Okay, well, how do I select this? Okay, well, I can select the 1 and the 9. That's valid. I can select the 3 and the 27. And I can select the 1 and the 27. All of these 3 are fine. So there's 3 ways to select from there. I can't select 1 by itself because, as previously explained, I've got to choose the maximum number of elements. I can't select 3. There's no combination of 3 that I could select because they would break the rule that one element is 3 times the other. And I obviously can't select 4. So now I got to multiply this by this, by this, by this, by this. The good news is the 1's don't contribute to the product, so the 1's can be ignored. So that means I've got 3 times 2 to the power of 4, and that is 48. So that means there's 48 triple free subsets when k is equal to 27. And also, I hope you can notice that this number is in that form that they gave right here, p to the a, q to the b. So q to the b. So to calculate n, you just have to figure out p squared plus q squared plus a squared plus b squared, and that's very easy to do. Okay, so now that we've done two examples, one with k equals 9, one with k equals 27, I think we are ready to tackle the big guy. So here we go. So now we're going for the big one, all the way to 2045. So remember, 1, 2, 3, all the way until 2045. We have to now create the system. And in this case, k is equal to 2045. So here we go. Just like before. Start with 1, and then we have 3, 9, 27, 81, 243, and 729. And then anything above that, it would exceed the 2045. Now, here I'm going to write how many elements there are. And in this case, 1, 2, 3, 4, 5, 6, 7. So 7 will go here. And then here, I'll write how many, the number of such subsets. Well, I have to fill out the list first before I figure out how many there are. Let's try with 2. 2, 6, 18, 54, 162, 486, and 1458. Okay, that's another 7. And then let's go to the next one. Skip over 3 because 3 is already included. The general rule would be that nothing in the first column would ever be a multiple of 3 because those will already have been included. So just keep that in mind. That's actually a pretty important rule. Okay, with 4, 12, 36, 108, 324, and 972. Okay, well, this is 1, 2, 3, 4, 5, 6. Oh, okay. So that means we are now down to 6. So that means the ones that have 7 elements, there's only 2 of them. All right, so that is how we're going to do this. Now, I know it may seem like extremely time-consuming, but the good news is that it gets quicker. And you have to do a little bit of number crunching. So you make these lists as follows. So these ones you can continue. I'll just write them out. And as you continue to make this list, you find out quickly that you only have 4 that have 6 elements in it. The next ones have 5 elements. And then you just continue to make this list, dot, 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 like that. And then you'll get to 25, 75, 225, 675, and then 2025. This will be the last one of 5 elements. And you can count these up. There's not that many. There's only 11. Now you say, well, I actually see that there's more than 11. I see 16. How did you get 11? Well, here's a little bit of a trick you can use to get that 11. What you do is you take this number, 25, subtract from it 1 below that. So that's 9. And that gives you 16. Yes, there's 16 numbers, but we cannot include multiples of 3. So how many multiples of 3 are there among 16 numbers? Well, it would be 16 divided by 3. And just like the previous question, you have to take only the integer value. So it would be 16 minus 16 divided by 3 bracket, and that's 16 minus 5, which is 11. So as previously, I got 11. And that's a quick way of doing it. And then you just keep doing this. You just keep going like this all the way through. So same thing. So now we've done the 7 element sets, the 6 element sets, the 5 element sets. Now probably we're going to get down to 4 element sets. 26, 78, 234, and 702. And that is indeed 4 elements. And then you dot, 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 keep going until you get to the last one, that's 474. And that is going to be a 4 element set. And how many are there? Well, this is where you use your fancy trick. 74 minus 25. All right, so that is 49. And then 49 minus 49 divided by 3, the integer value. And that will give me 49 minus 16, which is 33. All right, great. Let's keep going. Now I'm at 76, because remember, 75 is a multiple of 3, and it's already here, so I can't include it again. So a little bit of thinking involved here. Not an easy question, but completely realistic. Okay, this is a 3-element set. And similarly, dot, 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 you keep going until you don't get any more 3-element sets. And 227 is the last one that gives you 3 elements. And now we have to figure out how many of them were 3 elements. Okay, 227 minus 76. 75, not 76. Remember, it's got to be one less. Okay, and that is 152. And then you do 152 minus 152 divided by 3, the integer value. And that is going to be 152 minus 50, so 102. All right, let's keep going. 228, I believe, is right here, so can't use it again. It's a multiple of 3. So we got to start with 229 and 687. So now we're down to 2. And then the biggest one is 680, 2040. And then that's it. All right. So again, 680 minus 228. And that is 452. And then, of course, 452 minus 452 divided by 3, the integer value. And that gives me 452 minus 150, so 302. All right, now we have to figure out one final column of a table. And that is, for each of these, what is the maximum? So I guess what I'm really talking about is choices. How many choices? What are the choices? So I'll start off with this end of the table. I think it's a little bit easier to explain. So when you only have 2 elements, you can either choose this guy or this guy. So for each of those, you got 2 choices. So I'll just put 2 right here. Okay? When there's 3 elements, if you remember, there's only 1 choice. And for example, you can only choose 227 and 2043. That's it, as previously explained. When there's 4, I think I had done that one too. You can have 3 choices. For example, if this was the subset, your 3 choices would be, or let's go with this one. It doesn't really matter. You can use either 26, 234. You could use 78, 702. Or you could use 26 and 702. So these 3 choices are why I put a 3 there. Okay, now we get into the new territory, which is this guy. 4 elements we did. Now we have to do 5 elements. Well, when there's 5 elements, interestingly, there's only one way of choosing. For example, if we have, say, this guy, we can only choose 10, 90, and 810. That's the only way of doing it. To choose the maximum and to choose in a way that the rules are satisfied, that no element is 3 times the other. All right, moving right along. If there's 6, well, there's going to be a little bit more complicated. So let's explain with that one. If there's 6 elements, there are 4 ways of choosing. So for example, you can use 4, 36, 324. You can use 12, 108, 972. You can use 36, and 972, or you can use 4, 1081, and 972. And as you can see, there are 4 of them. That's why I put a 4 there. So I hope this is making sense. And one last one has some good news. that there's only one way of doing it. So for example, if this was the subset, you can only choose 1, 9, 81, and 729. That's it. That's the only way to do it. So that's why there's 1 there. Okay, we are in the final step. We are basically at the point where you calculate n. And just like before, if you remember, with my examples where k is equal to 9 and k is equal to 27, that's the same way I'm going to do it up here for this one. N is going to be, I'll do it in red here, this to this power. So 2 to the power of 302. This to this power. But we don't really need to include that because 1 to the power of 102 is just 1. It's pointless to write that in. So I'll skip that. Then this to this power, that will actually contribute. This to the power of 11, don't need to put that in. 4 to the power of 4, that will definitely contribute. And then 1 to the power of 2, which is just 1. There we go. That's the value of n. And we can simplify this a little bit. Since this is 2 to the power of 2, this basically becomes 2 to the power of 310, 3 to the power of 33. And that is of the form p to the power of a, q to the power of b. And now our final step is to figure out big N, which was p squared plus q squared plus a squared plus b squared. Well, that's going to be 2 squared plus 3 squared plus 310 squared plus 33 squared. That number is 97202. We were asked to find the last 3 digits, 202. So the answer to this is 202, which is choice A, number 25. Lateral PQRS diagonals PR and SQ intersect at O inside PQRS. SP is equal to SQ is equal to SR is equal to 1. And angle QSR is equal to 2 times angle QSP. Mark determines the measure of 12 angles that are the interior angles of triangles POS, POQ, ROS, and ROQ. The measures of each of these angles in degrees is a positive integer, and exactly 6 of these integers are prime numbers. How many different quadrilaterals have these properties and are not rotations or translations of each other? We need a big version of the diagram because this question is all about angle chasing. And angle chasing is very common on math contests, and they oftentimes put these kinds of questions in. So here we go. We are told that this angle is twice this angle. So I'll call this 4 theta and I'll call this 2 theta. That was given in the question. Now the rest I've got to figure out. But there's some good news. We are told that this is equal to that is equal to that. So they've got some isosceles triangles, right? So let's start with this one here. If this is isosceles, this is going to be equal to that. I'll just call them x for now. So from the first triangle, I know that x plus 2 theta plus 4 theta is equal to 180. So that means 2x is equal to 180 minus 6 theta, and therefore x is equal to 90 minus 3 theta. Okay, I'll put that in here, 90 minus 3 theta. And this one also, 90 minus 3 theta. Let's keep going here. We got quite a few angles to get. So where do we go next? We have another isosceles triangle, this one right here. And therefore this angle has got to be the same as that angle. This angle I called x, so this angle here I'll just call y. And therefore this was going to be x plus y, right? Because this angle is the same as that angle. Okay, again, angle chasing. So let's see, I guess we're using this triangle. So that means 2 theta plus x plus y is equal to 180. And x we actually know. So it's 2 theta plus 2x, but x is 90 minus 3 theta. So that would be 180 minus 6 theta plus 2y is equal to 180. So that means 2y is equal to 4 theta, and therefore y is 2 theta. Okay, that's a pretty good result. So that's 2 theta right there. And I guess x plus y would be 90 minus theta. So there we go. Okay, where do I go next here now? Might as well figure out this one. I'll just call that z, and by opposite angles, that's going to be z. Yeah, that's a pretty good way to go about this. And then we can just use this triangle. So in that triangle, more angle chasing, 2 theta plus 90 minus theta plus z is equal to 180. So let's see what that gives me. Z is equal to 90 minus theta. Okay. 90 minus theta. And this one also, 90 minus theta. Where do we go next here? W is the letter I guess I'll choose for this and this. Those will be both W's. W and W. And for W, I guess we can just use the whole way around, that everything is going to be 360. So 2W plus 2Z is 360. And then 2W, well, Z is this guy, 90 minus theta. So 180 minus 2 theta is 360. So 2W would be 180 plus 2 theta, and therefore W is 90 plus theta. All right, 90 plus theta for W. Do I have any? Yeah, I got to get this one and this one. Okay. All right. Okay, the good news is that's part of this isosceles triangle. Okay, that is indeed good news. So this angle here, I'll just call whatever V, and therefore this has got to be the same as this one. So this angle will be X plus V. And I think that's it. That would be the last one. All right, here we go. Last angle chasing formula. And which are we going to use here? I guess we can just use the big one, that whole triangle. So that means 4 theta plus x plus v is equal to 180. And then we figured out one of these, right? X, yeah, we figured out x a long time ago. So 90 minus 3 theta. So this is going to be 4 theta plus 2x, so that's going to be 180 minus 6 theta. Plus 2v is 180. So that looks like 2v is going to be equal to 2 theta, and therefore v is equal to theta. All right, that's a pretty good result. So I think I have them all. I have them all, and we'll just make a list now of all my angles. I've got, let's just keep the diagram in the picture here because I've got to use it. Let's see here. In this triangle, I've got 2 theta, 90 minus 3 theta, and W. And what was W? W was 90 plus theta. All right, 90 plus theta. And then in this triangle here, I have 4 theta, x, which was 90 minus 3 theta, and z, which is 90 minus theta. Okay, and then in this triangle, I've got v, which I just figured out was theta, and then x plus v, which I guess would be, x is 90 minus 3 theta, and then v is theta, so 90 minus 2 theta. And then the other angle is w, and w is equal to 90 plus theta. And then the last triangle, which is this guy, those angles are z, which is, or y, which is 2 theta, and then z, which is 90 minus theta, and then x plus y, which is 90 minus theta. All right, great. These are the 12 angles. Now, there's 12 angles, but some of them are repeats, right? So, for example, theta is listed once. 2 theta is listed twice. 4 theta is listed once. 90 minus theta is listed 3 times, actually. Yeah, 3 times. 90 plus theta is listed twice. 90 minus 2 theta is listed once. And finally, 90 minus 3 theta is listed twice. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. Okay. Now, the rule is that 6 of these must be prime. 6 of these have to be prime. And we've got to figure out how to do that. Okay, so let's make a table with these angles. Here we go. Now, I got to start somewhere, right? So I'm going to start with theta. And I've got to make sure that they're prime. So we're going to start with prime numbers. And the first prime number, of course, is 2. And then I'm just going to list prime numbers. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and hopefully, I don't have to go beyond that. Now, here's the thing. This is a big table, and it's very time-consuming, right? The math is not that hard, but it's just time-consuming. But some of these I don't need to fill out. Why? Well, because 2 theta is not going to be prime. It's divisible by 2. It's 2 theta. 4 theta is obviously not going to be prime because it's divisible by 4. So I don't need to worry about those guys. 90 minus theta, 90 plus theta, that one I need to figure out. 90 minus 2 theta, you can factor out a 2. So that's going to be divisible by 2. That can never be prime, therefore. And 90 minus 3 theta is going to be divisible by 3. You could factor out a 3. So the only columns I need to figure out are this one, and this one. So that's what I'll do. So we got 88. And the math now is very easy, right? So it makes it very quick that we can do this. 85, 95, 83, 97, 79, 101, 77, 103, 73, 107, 71, 109, 67, 113, 61, 119. Now we want a situation where we have at least 6 primes. Okay, well, there's only one of these guys. 90 minus theta, there's 3 of those. And 90 plus theta, there's 2 of those. So if we have prime, prime, and prime, we'd have 6, because it'd be 1, 3, and 2. Okay, let's see. Which one of these are prime, prime, prime? And when I look through the list, I think we have a right here. This one, the 19 gives me, so does 23, and so does 29. Is there any more? And the 11 one, this one also. Yeah, that'll do it. This is divisible by 2, that's not prime. 9, this is divisible by 3, this is obviously divisible by 5. And 77 is obviously divisible by 7, so those are not primes. So that's it, I get 6. And if you keep going, you'll find that you won't get any more. All right, we're done. Time consuming, definitely. So 6 I got. And therefore, the answer to number 25 would be choice D. P, Q, R, S, and T are 5 different integers between 2 and 19 inclusive. Which number is the largest? Let's go through each of these. First, let's list all the integers from 2 to 19. And then we can talk about each of these one by one. P is a 2-digit prime number whose digits add up to a prime number. Well, let's first of all talk about which of these are 2-digit prime numbers. The 11, the 13, 17, and 19. Which of those has digits that add up to a prime number? 11 is 1 plus 1, which is 2, and 2 is a prime number. So P, immediately we figured out, is equal to 11. So there we go. Q is a multiple of 5. Okay, so Q's got a few choices. It can be 5, 10, or 15. So Q can be either 5, 10, or 15. R is an odd number but not a prime. So it's either 3, 5, 7, 9, 11, 13, 15, 17, 19, but not a prime. So it can't be 3, 5, 7, but it can be 9, because that's not a prime. Can't be 11 or 13, but it can be 15, and it can't be 17 or 19 because those are prime. Okay, let's look at number 7, S. S is the square of a prime number. All right. So squares of primes. 2 squared is 4. 3 squared is 9. And then 5 squared is 25. And 25 can't be possible since we're only going up to number 19. And then T is a prime number that is also the mean of P and Q. Okay. So if P is 11 and Q is 5, the average would be 8. But 8 is not a prime because T has to be a prime number. So that means Q cannot be 5. Let's try 11 and 10 for the value of Q. And we get 21 divided by 2 is not even an integer. So Q cannot be 10, therefore Q must be 15. And if it is, then the average is 13, and that is indeed a prime, so therefore T is 13. So P is 11, Q is 15, T is 13. And then remember, all of these are different, so that means R cannot be 15 since Q is 15, so R must be 9. S therefore cannot be 9 since R is equal to 9, so S is 4. So there we go. We got the values for all of the P, Q, R, S, and T. Now they're asking which one of them is the largest. Well, the largest is Q, since it is equal to 15. So number 21, the answer is B. The product of n consecutive 4-digit positive integers is divisible by 2010 squared. What is the least possible value of n? So they're saying you've got some numbers. There's n of them. And they're all 4-digit numbers, and when you multiply them together, you've got this big long product, and it divides by 2010 squared. It gives you some integer. Okay, no problem. So that means that this number in the numerator has to include all of the prime factors of 2010 squared. So that is the first task of figuring out what is 2010 broken down into prime factors. It's 2 times 3 times 5 times 67. So if you have 2010 squared, it's basically 2 times 2 times 3 times 3 times 5 times 5 times 67 times 67. So this numerator up there has to include all of these guys. If it does, when you divide by 2010 squared, it will give you an integer. Okay, so let's figure this out. First and foremost, this is a very important point that they're 4-digit numbers. All the numbers that I put in my numerator, they have to be 4-digit numbers. So I have to first start off with creating a 4-digit number from these prime factors. And if you notice, these are very small numbers. Interestingly, even if you take all of them and you multiply them together, you actually still don't get a 4-digit number. You get 900. So the only way to get a 4-digit number that includes the prime factors is to involve the 67s. So obviously one such number would be 67 times 67. That's definitely going to be one such 4-digit number, and that number is 4489. Now, I think the challenging part of this question is that you can also create another 4-digit number as a reference point by including a 2. Because if you do 2 times 67 times 67, you will also get another 4-digit number that can be used, and that's 8978. You can't go any higher because if you started using 3s and 2 67s, you would no longer have a 4-digit number. You'd have a 5-digit number. You'd have 13,000 something. So these are the only 2 4-digit numbers. So my string of 4-digit numbers that I put in my numerator has to be somewhere plus or minus those numbers. So first, let's just start with this guy here. And let's see what we get. All right, so we're going to start with 4, 4, 8, 9. Now, I don't know which direction we're going. Are we going greater? Are we going less? So I'll just write in a few on either side. All right, now let's play this game here. My task is to involve all of these guys into a string of numbers that obviously includes 4, 4, 8, 9 as my sort of reference point. Well, let's see. Okay, so I've got to ensure that every single one of these prime factors is included in the numbers that I choose. So I'm starting with 4, 4, 8, 9. So 4, 4, 8, 9 is obviously divisible by 67. It was 67 divided by 67. 67 times 67. So that means this guy takes care of this guy and this guy. Okay? Now we can go in either direction. We can go this way or that way. It doesn't really matter. I'll just go this way, and then we'll see what happens. 4, 4, 8, 8. Well, that is obviously divisible by 2, and it's divisible by 2 once again. So it takes care of 2 2's. Now, can it be divisible by anything else? And the answer is yes. It can also be divisible by a 3. So this one helps us out quite a bit. 4, 4, 8, 7. Is that divisible by any of the remaining 3? 4, 4, 8, 7 is not divisible by 5, obviously, because it would have to end in a 5 or a 0. And it's also not divisible by 3. So that's a loser. How about 4, 4, 8, 6? Does that help me in any way? Is it divisible by 3? It's not. So that's a loser also. How about 4, 4, 8, 5? Is that divisible by 3? Yes. Is it divisible by 5? Yes. So this takes up that one and that one. Now, if I go in this direction, that's obviously divisible by 5 since it ends in a 0. So there you go. This string of 1, 2, 3, 4, 6 numbers, they're consecutive 4-digit positive integers, and when you multiply them all, they will all contain those factors which represent 2010 squared. So far, the answer looks like it could be 6. And in the answer choices, 6 is the second smallest. Oh, I see. So, it's possible that 5 could be the answer, so we got to keep going here, unfortunately. I was hoping that 6 was the smallest, but it's not. Okay, so let's go in this direction now. All right, we're going to obviously keep this 4, 4, 8, 9 because that takes care of 2 67s. Now let's go to 4, 4, 9, 0. 4, 4, 9, 0 obviously is divisible by 5, so that takes care of 1, 5. And is it divisible by anything else? It is by 2. And then anything else? No, unfortunately. So far, we have those two. 4, 4, 9, 1. Does that contribute or help us in any way? Is it divisible by 3? The answer is yes. So that takes care of 1, 3. And it's divisible by 3 again. So I can circle another 3. 4, 4, 9, 2. Obviously, that's divisible by 2. Since it's even. And I think that's it. And then we've got this one lone 5, and unfortunately I have to go all the way to include this guy, and this guy to get a number that's divisible by 5, which is this. So that would mean 1, 2, 3, 4, 5, 6, 7. Oh, now I got n equals 7. So that's worse, because they want the least possible. Okay, so this is the part of the question that I think is tricky. We have to now do the same story for this guy. And that being 8, 9, 7, 8. Okay? And same thing, we got to go in either direction. So 8, 9, 7, 8, this middle number, it was 67 times 67 times 2. So it takes care of those ones. Now let's go this direction. Doesn't really matter, but let's just go in that direction. Does that help us in any way? Is it divisible by 3? It's not. Is it divisible by 2? No. And is it divisible by 5? No. So that doesn't help us at all. How about 8, 9, 7, 6? It's obviously divisible by 2 since it's an even number. And then Is it divisible by 3? And the answer is yes. And anything else? No. So we got a couple of prime factors. How about 8975? That is obviously divisible by 5 because it ends in a 5. Then it's divisible by 5 again. And is it divisible by the final 3? No. But what about 8974? Is that divisible by 3? And the answer is no. Okay. Well, what if I go in this direction and try the 8979? Is that divisible by 3? And the answer is yes. So look at that. By using this guy, I got a string of only 5 numbers that include all the prime factors of 2010 squared. So the answer is n equals 5. So number 23, the answer is A. Lynn chooses 4 distinct numbers 1 through 9 and arranges them to form the 24 possible 4-digit numbers. These 24 numbers are added together to give the result n. For all possible choices of the 4 distinct digits, what is the largest sum of the distinct prime factors of n? Well, in order to understand this question, I will give you an example. So we have to choose from these 9 numbers, right? So I'm just going to choose 4 numbers at random. I'll choose 3, 6, 8, 9. Now, these 4 numbers, from these, I have to make 24 numbers. Okay, I think I can do that. Let me just do it over here so I have enough space. 3, 6, 8, 9. 3, 6, 9, 8. 3, 8, 6, 9. 3, 8, 9, 6. And then 3, 9, 6, 8, and 3, 9, 8, 6. And so on, right? So I'll just make all 24. So here are the 24. You have 6 that begin with 3, 6 that begin with 6, 6 that begin with 8, and 6 that begin with 9. Now we have to add them all, right? Because these 24 numbers are added together to give the result n. Now when you add them all, that is when I think the understanding of the question comes. And of course, all of you definitely know how to add. I don't need to give you that lesson. So anyway, add them, something happens that is interesting in my opinion, that if you look at this first column, which would be the ones digit, you have 9 of those 6s. Sorry, 6 of those 9s. Then you have 6 also of the 8s. And then you have 6 also of the 3s. And you have 6 also of the 6s. And that, in this particular case, is 156. And then you add the next column, which is this column, right? That column is the tens column. It's the same thing. The only thing is you have to multiply by 10. And then when you add the next column, which is the 100, it would be the exact same thing, but this time you multiply by 100. And the very first column, which is the thousandths column, it would be the same thing. So if you add up all these guys, you would get n. And n looks to me like a very interesting pattern, that it's going to be 1,000 times 6 times the numbers added together, which in this case are 9, 8, 6, 3, plus 100 times 6 times the numbers added together, and then plus 10 times 6 times the numbers added together, and finally the number 6 times the numbers added together. So when you add those guys up, you can factor out actually the whole thing. You can factor out the 9 plus 8 plus 6 plus 3. You can factor out a 6, and what you're left with is 1,000 plus 100 plus 10 plus 1. And this, in our case, was 156. This is always going to be 6, and this is always going to be 1, 1, 1, 1. So we have to choose this in a way so that the prime factors of n add up to the highest number possible. Well, let's explain that in this first. What are the prime factors here? Well, 156, I believe, breaks down into 2 squared times 3 times 13. Six is just 2 times 3. And then 1111 is 11 times 101. If you combine these, you get 2 to the power of 3 times 3 to the power of 2 times 13 times 11 times 101. 101 is prime. So now, what is the sum of the prime factors? In this case, it would be 2 plus 3 plus 13 plus 11 plus 101. And that is 130. And that's just an example so that you can understand this question. So I've got to choose these 4 numbers in a way so that this becomes as high as possible. Okay, I think I can do that. So my n is going to be, I'll call those numbers A, B, C, and D. And then it's going to be times 6 times 1111. So looks like my prime factors right now with that 6 and that 1111 are 2, 3, 11, and 101. And then I've got to choose A, B, C, D in a way so that this number gets high as possible. Well, so far, what is the sum of my prime factors? So far, the sum is 2 plus 3 plus 11 plus 101, right? Just these guys. And that is 112 plus 5, which is 117. Okay, let's go back to our answer choices. They should all be greater than 117, and they are. Okay, so let's see if I can make this as big as possible. So how do I do that? Well, A, B, C, and D are chosen from this list right here. This list, the numbers 1 through 9. So I'll write those numbers 1 through 9 here. 1, 2, 3, 4, 5, 6, and then we'll kind of do trial and error. What's the largest sum I can make? Well, if I chose the largest numbers, if I chose 6, 7, 8, and 9, that would be the largest, and that is 30. Okay? If I put 30 in there, that's going to be what? 2 times 15, which is 3 times 5. Okay? So 2 is not unique. 2 is already here. It's very important for you to understand and read the question carefully that what is the largest sum of the distinct prime factors? So they've got to be distinct. If I use this, the 2 is already in there. The 3 is already in there. So the only new distinct guy I get is 5. And that would bring this up to 122. Okay, that's not very high. I think I'm pretty confident I can go higher than that. So to do that, I'm going to have to choose a number other than 30. Okay, let's try the next one down. 29. You can easily make that with any combination, 7 and 5. That would do it, right? If I put a 29 in here, 29 is a prime number. So that means the sum of the distinct primes would be what I've already written, 2, 3, 11, and 101, plus the 29. And that would bring me all the way up to 146. And that is one of the answer choices. That's D. But before I circle it, let me just make sure that there's nothing bigger than 146. And if I put 28, it would be basically, if I put 28 here, it would be 2 times 2 times 7, which would just add a 7. And that's definitely much less than 29. So you just got to be sure that you don't get anything greater than 146. And you can't, basically. No matter what you try, you won't be able to. So now that you're convinced, hopefully, that this is indeed the largest, that's the one you go with. So 146 is the answer, and therefore number 24, that would be D.